Okay, so what we have here is we have a DC motor control using bipolar transistors. So what's the main principle as to how this works? So the idea is usually you have a motor, right? And depending on the polarity voltage you're applying across this motor, you will get either a forward direction, which is clockwise, or you get actually it's counterclockwise usually. It's forward direction, and then clockwise would be a reverse direction of the motor. So how do you achieve this kind of reverse forward voltage control of a motor? You typically would use an H bridge. So I'm going to quickly give you a rundown as to like how the current path flows and the voltage polarity um, of this circuit will work typically when you're either applying forward or reverse voltage to this motor. So let's assume that this the left side of this motor, the left pin of the motor is the positive terminal, and the right pin of this motor is the negative terminal. What that means is when you apply a positive voltage at the positive terminal and a negative voltage at the negative terminal, which is usually just ground, your common node right here, you will get a forward voltage applied to this motor, and you'll get a forward direction of this motor. So that means that the motor will turn counterclockwise. So how do we do that? So the method is typically fairly simple. What you'll do is you'll have four MOSFETs like this. This is probably the most important part. These two MOSFETs outside are just the control from this VDC right here. The most important part is going to be this aspect. So these four transistors are essentially control the path of current flow of your positive voltage source. So let's look at this. What happens if we apply a forward voltage? So if we connect this voltage source high, and we connect it this way, what will happen is you will apply voltage to this MOSFET, or sorry, this BJT. I'm still using MOSFETs. This BJT will apply a positive voltage, which will then cause a VBE flow here, and that will result in conduction in this region. So this will conduct, which will allow VDC to essentially conduct into here and into here. So what that will do is this is a PNP transistor, so these are PNP on the top, and what will happen is in this scenario, applying a direct positive voltage to this transistor will open it. Applying a positive voltage to this transistor, NPN, will close it because it's an NPN. They work basically. They're like they're kind of like paired, so they work exactly the opposite of each other. So applying a positive voltage here will turn it on. Applying a positive voltage here into this base will open it. And then what we see here in this scenario, right? This is open. This is closed. This will then close this transistor. So this negative terminal connects to ground. And then on this side, so these two transistors are going to basically control the positive terminal of this motor. So this will essentially be open. This is off, so you have voltage going here. Actually, what the fuck?
Wait, when it's open, does that mean that it's off?
Yeah. Yeah. So it'd be off. What the fuck? That's actually that's kind of weird. This should be open, and this should be closed because there should be essentially be 0 volts here, if that makes sense. Sorry about that, guys. Yeah, so this would essentially be positive here, and then this would be negative here. And then when you connect to reverse, this will close, which results in this voltage here going it's going to essentially be 12 volts. So this is going to be open, and this is essentially going to be 0 volts, and this is essentially going to be in this section is going to be closed. So you're going to have 12 volts here like this, and then it will flow down through here. So if it's in through here, it will go like this, and then if it's down here, it will go like that. So it kind of you can essentially control uh, the direction. Actually, a better explanation would be to look at this. I think it's a lot easier to actually understand. So you see that if these conduct, these two MOSFETs conduct, then it will run positive to negative, and then if these are conducting, these two on these sides are conducting, then it'll go this way instead. So that's usually how it works in H-bridge. So there's like a lot of different kinds of circuits you can use. Um, I think I remember I found a better one. I don't really like that one, so I'll probably just uh, let me find you a better one. I also don't like that. Usually in H-bridge used to have diodes um, as well to protect the inductive load of a motor because a motor is inherently inductive because it usually uses an inductor inside. In the stator uses an inductor uh, kind of thing to control the rotor. So I wouldn't use this design honestly. I would probably go in with something more like this or um, something more like this. So let me go ahead and just like make this really quick. And then, do you guys have any questions though before I continue?
So it's better to use the enhancement MOSFETs over the BJTs.
Yeah, I think so. I think it's kind of dependent on like if you need amplification, because usually BJTs have a higher beta, so they usually have amplify better. But if you don't really need that and you just need to apply 12 volts directly at some amount of current that's already related to the motor itself, I would say just go ahead and use MOSFETs. Um, there's a really good. Actually, maybe I'll just use mine. But yeah, that's kind of it. Let me go ahead and pull out the. Let me stop streaming. I'm going to go ahead and um, yeah. So now that I have this project that I created, um, by clicking create project, you can either do so from the file menu as well, from the top left corner. You can click a new project like that, and then from here you can click right click here and then click add to project, and then you can click add schematic. So without wasting too much time, let me just go ahead and find the components that we need. So you can use manufacturer part search, or you can also find your components on Mouser. It's kind of the best options, really, like in any case. But let's look for something that's rated high enough to deal with like a certain motor that we're trying to drive. So let's do like sometimes the manufacturing part search won't have the component that you're looking for, so you'll typically have to find it on Mouser. Um, to do this, let's go ahead and find um, the kind of component that we're looking for. So let's say you don't really know what kind of MOSFET you want to choose. Sometimes you can go into, you can actually sort for them, which is pretty nice. So after searching up, after searching into the product section, semiconductors, discrete semiconductors, and then eventually getting into MOSFETs, or you can just search up MOSFETs in the search bar. It'll usually give you, it'll automatically like sort into this thing. You can find different MOSFETs that you're looking for. So this one seems to be rated for up to 40 volts, which is way above our 24-volt motor. The gate can only be controlled between 20 volts and minus 20 volts. So we'll have to use something lower voltage, like maybe 12 volts. And then we can also use, we can also find more about like what's the max current. So the drain current's very high. As you can see, this is like way over what we need, honestly. Like that's kind of crazy, not gonna lie. But yeah, up to 100 watts of power dissipation as well. So these are kind of like meant for motor drives, but like usually like larger motors, so it's pretty useful. And then in order to actually get this part, you just have to kind of like download it on using Semaxis. If you need help setting up Semaxis, you can usually find out how to download it by clicking here, and then it will usually tell you how to download, like this. This is, by the way, this link is actually also posted in the electrical subsystems pin, so you can see right here. I have it right here. So if you need to ever download this, you can just do so that way. And then I'm going to download that really quick. I'm going to log in. I'm guessing this is hidden. Okay, sick.
Oh, we know your password now.
Hey, what?
Where's your eye?
All right, so if you can't find it in manufacturing part search on the side here, when you click on panels, you'll be able to look for manufacturing part search this way. But if you're not able to find it through here, you can also source your parts from Mouser or anything online, so you can source them that way as well. So I'm using the Altium library loader from Semaxis. The way to download it, you can find all the instructions in the pins and electrical subsystems chat. But basically, I'm going to show you how to use it from here in Altium. You're just going to click Open ECAD Model, and usually you're going to use a have your downloaded compressed folder. You're going to just uncompress it. You're going to extract it all. And afterwards, you're basically going to use the EPW file, and it's going to automatically make the schematic and footprint libraries for you that way.
Roman, I'm just gonna follow along because my thing is glitching.
Oh, yeah, no worries. Yeah, so so you're gonna have your 4 MOSFETs like this, right? And then you're going to have you're gonna connect them like these two like that, and then you're going to connect these bottom legs are going to connect to your ground, since this is going to be the path to ground that you're going to need to use
To drain?
Yeah, to drain essentially the ground for your for the negative side of your motor. So the middle though is going to be like where you would see the like usually in the schematic we like to have it as like obvious as possible as to like what you're trying to do. So you could probably not even have it in this orientation. You could maybe make it smaller, but it's usually better to have it this way so that you can kind of more easily see like what the representation of your circuit is. So I'm just gonna leave it like this. So this would be like where the motor would actually connect to. So I'm gonna put 2 ports like that, and then I'm gonna put them like this, and I'm gonna label them so that we know which side is positive and which side is negative. So I'll call this like motor, and you can label it whatever you want. I'm just gonna call it motor P. I'm gonna put output, and I'll make this motor motor N as to refer to mode negative. So I'll make those both outputs like that, and I'm gonna label. I'm just gonna go like that, and I'm just going to put, now I'm gonna put my power port on the top here, and I'm going to call this P12 volts, and I'm going to wire that up like this. So we have essentially our main H bridge now. Now we just need to add the gate control basically for these 4 guys. So I kind of talked about this with the BJT implementation, but the MOSFET implementation is a little bit simpler. All you'll need to do is, if you want the motor to drive forward, you'll just need to turn this one on and this one on. So you'll have these two N MOSFETs routed in this way. Or actually, I would instead of using like instead of actually routing it all the way around this way, it would which would like kind of make the schematic like messy. I'll just use something called a net label. So if you right click on this wire symbol here and go down, you can just add a net label, and I'm just going to call this gate control P. So I call it that because it's the gate control for the positive when you want to drive the motor forward. Actually, I usually call it like this, like that, because like it's very like specific as to like what the gate control is for. So I'm gonna copy paste that and just put that here as well. And so essentially, when this goes high, when this GPIO pin goes high, it's going to turn on these MOSFETs, so the motor will drive forward like that. So it will drive like this, and then this will be your reverse. So this is gonna have to go low, and this is gonna have to go high, so that it drives that way. You can already see that this is a little dangerous because if these are high at the same time, then you short your supply, because if they both turn on at the same time, then you're cooked. So there are safety ways you can like have it so that you can usually put a fuse here so that if you short it, it just the fuse pops. For the time being, just because we don't have too much time, I'm not going to add the fuse. But if you're ever trying to implement this like in real life, please add a fuse here. I'm just gonna not include that for the time being, but I'll probably maybe include a fuse when I'm putting the connector for P12 though. But yeah, and then for this one, I'm gonna call it gate control reverse, just like that. And then these two, bottom. And then all we have to do now is we just have to move this up a little bit, like here, and then we just have to step up our because if we're using a microcontroller, they usually output on the gate only outputs like around 3.3 volts, or like the signal only outputs 3.3 volts, which should the voltage is too low to properly drive the gate of this MOSFET. Because if you remember a little bit about, I'll go a little bit over this later, but in order to properly pinch this MOSFET, you want this voltage GD needs to be like about 0, so you cut off any voltage, any current that could flow. So you kind of need a proper voltage to drive something like this as well. So you can just use a fairly simple gate drive circuit that I'll show you really quick right now. So it actually just involves another MOSFET. Really, that's all you have to do. Okay, so it involves a MOSFET and a resistor. That's it. And typically you'll have something called a gate resistor anyway, because these guys need like a certain, they kind of like draw a lot of current on initial startup. So usually apply a resistor to that anyway. I believe actually I would say it's better to actually have to explain once more though, this circuit right here is essentially just stepping up the gate drive of this to be 12 volts. It's kind of meant just to like properly like pinch off the so it's like fully off when you need it to be fully off. I think it's most important actually for PMOSFETs as well, because a PMOSFET the source is up here, so the GS has to actually be 0 volts to fully turn off. And if your gate voltage is too low, then it won't even turn off fully. So kind of just like, that's usually why you usually use a gate drive like this. You don't directly drive these gates from the microcontroller directly. So let me label this Q5 and I'll call this R1. And then let's use a port for this one because this is probably coming directly from our microcontroller. I'll just call this pin 1. And you can call it whatever you like, honestly, but I'll just call it that. Oh shit, this is an input, my bad. Like that, there you go. And then this will be our, let's just call this our gate control forward. Like that. And then we'll just, I'm just gonna copy this to use for the reverse gate control. And yeah, so now we have these two kind of gate drives. Now we just need to add now all we're missing is some diodes here. So you know how the diode, how we use like the diode for the relay, and you know in the BSPD, because I know you were kind of dealing with that. We use it as well for any relay actually. That's because the relay is an inductive load, and inductive loads can have voltage spikes when you suddenly open or close a switch, because it has to do with the IV characteristics of them, and because when you open the switch, you're trying to change the current really fast through the relay, and when the change in current is really large, then the voltage is also really large. It's kind of like because V equals L di dt. That's why. So it's kind of the internal aspect of why we have relays, or we have diodes usually for things like this. For inductive loads, always use diodes for inductive loads. Basically, you always kind of place it in a way that it's like your forward voltage, the cathode, so like the line will always be towards that, so that when the relay is trying to like discharge, it will essentially discharge the other way back. When you disconnect this, it will basically like have a path to run through. So usually you use something called a flyback diode for this kind of thing. I think we also use the 14148. I think is usable as well. I believe that's what we typically use. Yeah, these guys are through hole. Yeah, they're usually through hole. That's kind of fine. I think this one isn't through hole. Yeah, let's just use these ones because like you can use through holes if you want. You just need to. What the fuck? Okay, wait. Never mind. Okay, yeah. You can use through holes or you can use SMDs. It doesn't really matter too much. It just kind of changes the how we.
You have to make sure that the current is like. Actually, I don't even know because current goes through the anode, right, for the diode.
Yeah. This should normally be open. Like there should be no current flowing through this at all. The current should only flow through when you open this circuit, and this motor is gonna have an inductive load. It's gonna want to discharge the current through this like this way essentially when you open this. So there's like a path of current that it can flow through.
Oh wait, but like if the MOSFET's closed, but would the diode close too? Or
if it's closed, sorry, if it's closed, then there's the voltage should be open, right? Like this because the voltage here, well, the voltage here should be lower. Actually, Actually, it's better
Because
not
I
to think too.
remember
It's
something
better not to think
like
too hard about it.
this.
It's
I remember
exactly
something like this. It
yeah.
wasn't.
It's because the polarity of the inductor when it's discharging is reversed. So even though this is normally positive for it, when it's trying to discharge, it's gonna essentially uh, look like a I don't want to say battery because that's usually a capacitor looks like a battery, but it's more like the current is going to want to flow through this way. And if this is closed, then the current is going to just flow through this way. So it's going to essentially go through here. But when this opens suddenly, there's no path for the current to flow. So it's going to want to like really quickly discharge its current back through here. So it will have a high voltage. So the voltage across this should normally be zero, but when the voltage tries to spike, so it tries to go above this voltage here, it will essentially the voltage difference from here will essentially make it forward bias. So it'll go like that, and it will basically cut off the voltage to be equal to whatever this voltage drop is. So it will just like it will limit the voltage spike to just the voltage drop across this. If that makes sense, because diodes have a
For the,
voltage drop like when you they're not ideal, right? Like when you apply voltage across like in forward direction, the voltage to here will be like some kind of voltage. Like it will be like maybe 1 volt or 1.4 volts. Like so it will actually like limit um, the maximum voltage this can actually be as it's discharging current from the inductor. So this voltage will just be set. It'll just be forced essentially to a voltage higher than this voltage, exactly whatever this voltage drop is. Essentially, it's kind of like black
so
magic, Loki, but that's sort of what it is.
This isn't. This might be a stupid question. Is it basically just a resistor but for voltage?
Yeah, actually, that's a good way to think about it. I guess so. I guess the other thing though, because a resistor, yeah, I see what you mean. Yeah, I guess it could be like that. Yeah, I never thought about it that way, but yeah, sort of. Sometimes they're not quite resistors. I think they're resistors in this, like they're voltage resistors in this scenario. But sometimes diodes can be used in other methods, and like sometimes the voltage drop across it isn't necessarily like wanted. Especially if you don't want a voltage drop, like if you're trying to power load, then it can be an issue. But yeah, in this scenario, yeah, they kind of limit how much voltage can drop directly from this point to this point. So yeah, in this scenario, it's a voltage drop. But like if you had a resistor here as well, like for example, an LED, then it really isn't actually like limiting the voltage in that way. It's kind of like the voltage will drop through the resistor, and the voltage will drop through the diode as well. So you have to kind of like take both voltage drops into account using KVL, if that makes sense. But yeah, you have to use this for KVL. Yeah. What's up?
that's forward bias, right?
Yeah, so I'm referring to it when it's in forward bias. Normally, it should always be in reverse bias because like the voltage here and here should basically be the same because this is conducting, right? So the
Right.
voltage here will basically be zero. Like the voltage difference will be zero. So there's really no reason for this to conduct normally. But if you were to open this circuit suddenly, the voltage will try to spike really high from this point with respect to ground. So it will essentially have a pathway for current to flow, and the voltage drop across this to here will be limited by this diode. If that makes sense. So yeah, it's like a voltage resistor essentially, but it uses
Is that like the clamping or whatever it's called?
yeah, it's clamping exactly. Yeah, that's what we refer to when we say voltage clamping. Yeah.
So for the gate control reverse, are we gonna have to use a reverse bias diode, or is it still gonna be forward bias?
It's going to be a reverse bias diode. Yeah, so it's going to be the same way like this. So they'll all look exactly the same in all scenarios like that. And that basically protects all of these MOSFETs from exploding.
Oh, wait, that's a reverse bias?
Yeah, so it's reverse bias like normally. Like it's with respect to your P12. So when you're measuring P12 with respect to ground, then this should be a reverse bias. Like it should be open essentially, right? But when you're suddenly disconnecting this load by opening this MOSFET by lowering this gate, right? the voltage is going to want to spike suddenly with respect to ground. So this will no longer be reverse bias. It's going to want to essentially flow through here, if that makes sense. Like this will be higher than here, and it'll be since this voltage has to be clamped to whatever the voltage drop is. The voltage here cannot be higher than if you think about KVL, like it will essentially be this voltage here will be equal to like this the voltage drop of this diode plus P12, if that makes sense. Like going across like a loop, right? Like it'd go like this around.
Yeah.
If you think of KVL, like that's what it would basically be like clamped to. That's what when we say clamping circuit, like what Noah mentioned, like that's what we're referring to. We're saying that the diode is essentially clamping the voltage across it because of that. Actually, diode clamping can be used in other methods as well. Like we use Schottkys as well to clamp voltage drop in reverse bias as well. Because the if you try to apply a voltage larger here, larger than here, it will actually start to conduct, or no, it opens the circuit. But there's this thing called like reverse breakdown voltage, which I don't want to get too deep into that. It's a little complicated. But reverse breakdown voltage just means when the voltage across from here to here in the reverse direction of this diode is really large, there's a point where it starts to actually conduct like a regular forward conducting diode, and then it limits essentially the voltage drop across it to whatever that reverse breakdown is, if that makes sense. Low-key might be easier if I just show this to you. So you see how once you get to voltage breakdown, it starts to essentially just the voltage for changing in current, the voltage will just kind of stay the same. Kind of how like the same clamping here and voltage forward, like no matter the current change, the forward voltage across it just has to kind of stay the same. That's sort of what diodes do, right? Like they force a constant voltage, so you can actually clamp them in both directions, if that makes sense.
So reverse diodes are just when you get a negative voltage, and forward is just positive voltage.
Yeah, exactly. So in this scenario, it's actually clamping in the forward direction because like you only want it conducting this way. But if like, for example, if you're trying to clamp the voltage, like if you're trying to clamp this voltage on this side and it's connected to the reverse bias, it would only clamp when you get to this point on the IV carrier, like when it gets to VBR, which is usually like really large. So you have to find like a Zener. So that's why there's different types of diodes. Like if you're ever looking around, you'll see like this one is probably a Schottky diode. Like there's different kinds of diodes. This is actually a rectifier diode. So these are actually specifically for clamping like inductive loads and shit. But like you might find things like Schottky diodes and like Schottky diodes or Zener diodes. So a Zener diode just means that its breakdown voltage is really low. Like this voltage here is really low, so that you can kind of clamp it at like whatever you want essentially at that point. But yeah, normally diodes breakdown voltage is really large, which is why like when you're trying to clamp some kind of voltage in your circuitry, you kind of have to like look into the character, like the data sheet, to understand like I need this or you can filter for like specific breakdown voltages or specific forward voltages and stuff like that.
Bro, Zener diode was literally on my fucking final.
Yo, yeah, no, Zener diodes are really useful. Like they use it all the time for different things. Like if you're trying to, yeah, Zener diodes are just amazing. Honestly, they're used for like essentially like if you're trying to keep like your 12 volts essentially, when it starts to conduct, it'll just basically clamp it to that voltage. So a 12 volt Zener will essentially clamp your voltage at 12 volts no matter whatever this is. So they're used for like regulating voltages and stuff like that. So they're like really good and really nice. So that's kind of what we use them in the actual real world. So yeah, I think that's enough yapping. I think you guys can kind of do the rest. Kind of, I think the last thing we now have to do is just add like the connector. You can either make a separate connector. Actually, just for good habit, I would make a separate connector sheet, since that's usually like the best way for like if someone wants to like look at your project, it's easier to have a separate schematic for connectors, right? So that's what I would recommend. But yeah, so your connector will just need it. You can have essentially like two connectors or one connector, up to you. But if you had two connectors, you can have one 2-pin connector for your MCU pins, and then you can have another 2-pin connector for your motor. I would probably recommend that just from like uh, perspective of like separating use cases. So like this is one grouping, and this would be like another grouping, right? So that's kind of my strategy when I'm thinking about connections for a PCB. But it's kind of up to you guys. You can do a 4-pin connector as well. It's not really like not really. It's kind of up to the designer really. But yeah, if you guys want,
I have a question.
yeah, what's up?
Can you re-explain just the circuits that are on the left side with the MCU? Like,
Oh
what's
yeah,
their purpose again? Is it
yeah.
just like to keep a constant current?
Uh, Yeah, kind of. These are actually it's called a gate drive circuit, but it's actually used in a lot of different things. All it's really doing is it's taking this MCU pin, right? This MCU pin is probably going to be a signal pin that's either 3.3 volts or 0 volts, right?
Mhm.
Depending on what your logic is. So it's like a digital pin. So it just switches between those two voltages, right? Normally, the problem with usually gate driving, like when you're trying to drive the gate of this MOSFET as a switch, right, is usually have to apply a certain amount of voltage to it to turn it on, and it's usually dependent on a few things. In this scenario, um, it can be useful because like if you want this to turn on, actually, I'm
Well, I think
thinking
I let you understand it
yeah,
now.
it kind of like just turns on. Yeah, yeah, you kind of figure. Yeah, it's just
It's
sort of
just instead of
voltage.
using the actual pin or the signal from the MCU, it's just like using a 12-volt one, right?
Yeah, exactly. So when this goes high, this will turn
Just
on,
turns
and
it
this will
on.
go low. So
Yeah.
this will be 0 volts, right? Because it will essentially the voltage drop across this will be 12 minus 0. So it will actually drop voltage. So this will conduct, and this will be 0 volts. But if this was to be low, then this voltage if this goes 0 volts, then this will be off, so it'll be open.
Yep.
Yeah, and
Yeah.
then this will you'll have 12 volts sending straight into your gate. So it'll be like a higher. You're just kind of stepping up the voltage to your gate. Um, it's not necessary. I think this would actually work fine with just a 3.3 volt directly drive, but usually just having like a higher voltage drive is kind of it can be better sometimes for switching, like for fast switching or for higher load switching and stuff like that. But yeah, because essentially you have to also look in the sorry.
It's like whatever will close or open the actual
Yeah,
gate on the MOSFETs in the H bridge.
precisely. Yeah. So usually with MOSFETs, the IV characteristic looks more like when you apply a higher voltage VGS. The oh yeah, this one right here. Like the higher your VGS is, like the more drain current you can have. So it kind of just increases the amount of current you're able to supply to your load, which is typically why you see stuff like this. Like you don't directly drive this 3.3 volt on this gate
Yeah.
directly, because you can just like power the gate higher at a higher voltage. It's kind of it,
Okay.
yeah.
Yeah. Sorry, I realized that as you were saying it,
Alrighty, so as you can see here, I just quickly added one connector, J1, has the two MCU inputs here, and then I have a separate connector here for the motor outputs, just right here, and I separate them that way.